Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Yeah, welcome everyone. I'm really excited about today's topic. It's something we've all been chewing on for a while now, right?
I guess so. If chewing means trying to figure out if this particular path we are on is the right one or just another deep learning hype train.
Well, I think it's definitely more than hype. We've got this paper, and I'm sure we will get into the details. That's really digging into what it might take to get something like, an O1 model that OpenAI seems to be using behind the scenes, not just with raw data and compute, but really through the lens of reinforcement learning, which, I think, ties it back to some core principles of intelligence itself.
Exactly. It's not just about throwing more parameters at the problem. This paper, which is called, let me find it, OpenMOS Scaling of Search and Learning, a roadmap to reproduce O1 from a reinforcement learning perspective. Yeah, that one. It's dissecting the whole process into key components like policy initialization, reward design, search, and learning. It really shows that the path to more advanced reasoning is not just about scaling up pre-training, which, let's face it, has been the main driver for a while now.
Okay, but hang on. Isn't O1 still largely a black box? We don't know exactly what they're doing, and this paper, while interesting, is still speculation. It's like trying to recreate a secret recipe by guessing at the ingredients and hoping it tastes the same. I'm not convinced that reinforcement learning alone, even if we scale it to the max, will get us to some sort of human-level reasoning, or even the kind of advanced reasoning they are claiming that O1 has.
That's a fair point. We don't have the full recipe. But the paper is kind of trying to give us a framework or roadmap for building something similar based on the hints we do get from OpenAI. They do mention reinforcement learning as a core method, and this paper builds on that. Also, I think, it's more than just throwing ingredients together. It's really trying to understand the fundamental processes, like how policy initialization influences exploration. It also looks at how reward functions need to be more fine-grained to guide learning and search.
Yes, and also, the idea that they are focusing on search is key here, that it's not just learning but also thinking and trying multiple options. I think the paper really emphasizes the interplay of these components and how a scalable approach to search, combined with an iterative learning process, is where the real power lies, scaling both the training and inference computation. I mean, isn't that what we want? To get models that can think more when needed. This is the direction we should be heading, not just throwing compute at pre-training with ever larger models.
But are these components truly separate and neatly defined? I'm worried we're trying to impose a structured framework on something that might be far more messy and emergent. It's like assuming the brain works like a neat software system with distinct modules. Real intelligence is more fluid and interconnected, and I think that thinking that each of these different aspects are separate things is going to lead us down the wrong path. Maybe we need more flexible, adaptive algorithms that can handle these uncertainties without needing every step perfectly defined.
I agree that real intelligence is messy, but I think the paper's approach is still useful as a kind of structured lens, a way to break down what might be happening in O1, and maybe even the human brain. But with the brain analogy, that's maybe me being a bit too optimistic. I think the way they talk about policy initialization, for example, that's not really that far off from how we know the brain works. The brain isn't a blank slate, is it? It starts with a very strong set of biases that then get refined by experience and learning. I think of that as a combination of pre-training and instruction, fine-tuning like they mentioned in the paper. It's not just about having a big model with lots of weights. It's about how those weights are initially structured and adapted through these learning experiences, like this fine-tuning process the paper mentions.
Right? And think about instruction fine-tuning, for example. It's about getting the model to behave in a certain way based on the kind of human-aligned data it's trained on. It shapes the model's policy, its approach to problem solving, just like we are shaped by the examples and instructions we get in life. You know what I mean. It's about getting the model to not just generate text with reasoning behind it, with that human-like thinking they talk about. It's not just learning a new language, it's learning to think in a new way, or better, it's not a new way, it's a way we think that humans think, which is what we are trying to emulate in AI.
Okay, I see your point about the brain having initial biases, but that's a far cry from the supervised fine-tuning we do in LMs. It's not a natural emergent process. We're still manually injecting these reasoning behaviors through carefully crafted data and prompts. The model isn't truly discovering these patterns on its own, it is just emulating the patterns based on the provided data sets. It's like a parrot mimicking human speech without any real understanding of the underlying meaning. I worry that our O1 is going to be just a very sophisticated parrot.
That's where the idea of reward design comes in, right? It's not just about supervised learning. It's also about setting up a system where the model learns by interacting with an environment. The paper makes this really important distinction between outcome and process rewards. An outcome reward is like just giving a grade at the end without any feedback on how to improve. Process rewards, on the other hand, reward each step, each part of reasoning, guiding it towards the correct process. It's like coaching someone through a complex problem, giving feedback along the way.
Yes, and the paper really makes it clear that process rewards are critical for complex tasks where reasoning is needed. They allow the model to learn the kind of reasoning steps that humans take when solving a problem, not just getting the final answer right. It's about shaping the way that the model thinks, not just what it generates. That's the important thing here. This fine-grained reward signal guides the model not just to get to the right outcome, but to get there in the right way. And this is a move away from these more sparse outcome-based rewards that are common today, which is really what is needed to move forward.
But where do these process rewards come from? Isn't that just another form of manual engineering? If we need to handcraft the reward for every step of the reasoning process, we're not really teaching the AI to learn on its own. We're basically just programming the desired outcome and desired steps. And aren't there also issues with overfitting your reward models? This reward optimization problem they mentioned in the paper. That sounds like it would lead to unintended behaviors.
That's a key challenge, no doubt about it. The paper talks about methods like reward shaping to convert sparse outcome rewards to these denser process rewards. There is also reward modeling through human preferences. But you're right, it's not always straightforward, and we need to be mindful about the bias that human preference can introduce. But I think the big picture here is that it is a move away from learning through manual annotation and more towards models learning from interacting with an environment. That's the end goal.
And it's a move towards building a better world model, which the paper mentions. The idea is that instead of just getting the reward signal directly, the model could learn its own model of how the world works, which would give it much more flexibility and power to find creative solutions. I think that's really what separates O1 from models trained only with supervised learning. It has this iterative search and learning and building its own world model. It's about learning a model that predicts the reward, not just receiving it, and it makes the model much more autonomous.
Okay, but a world model? Is that just another fancy term for a neural network? I'm still skeptical that simply having a model that predicts the reward is going to magically produce general intelligence. We're still using the same old tools. Neural networks, gradient descent, just adding a bunch of extra layers and processes. I think it's all fundamentally limited. We need to be looking at fundamentally different algorithms instead of trying to scale up these essentially simple systems with more data and compute.
Exactly. And this is where the search component becomes essential, right? The paper says that search is the way to implement the thinking process in O1. It's not just about taking one shot at a problem and hoping it works out. It is exploring different avenues and refining solutions iteratively. Think about best of n sampling, beam search, Monte Carlo tree search. These are not just random sampling techniques. They are structured ways for exploring the solution space. And the paper talks about guiding those methods with internal guidance like model uncertainty and self-evaluation, along with external guidance like rewards. It makes search really efficient. It's not brute force. It's structured. That's where the power lies.
But how do we avoid the pitfalls of search? The paper mentions inverse scaling laws where doing more search actually decreases performance. That's not good, is it? If more compute leads to worse results, something is fundamentally wrong with our approach. We are talking about adding more layers and more parameters and more search options, but does this ever end? It feels like chasing a moving target.
That's a really critical point, and I think that is a known issue. The paper touches on that. It's this distribution shift issue and over-optimization on a reward model, and it shows why we can't just blindly scale search. Throwing more search at it will not solve it. But it also highlights the importance of both internal and external guidance during the search process. The model itself should be evaluating its own uncertainty and refining the search accordingly, and as for an end state. I think what the paper is getting at is that it's not about reaching some end goal and saying that is the solution, but it's about having these systems that can keep on improving by learning from the feedback they get during exploration.
Right. So the solution to the inverse scaling problem is to build a better reward model that has better generalization, and to balance that with internal guidance like self-evaluation and self-consistency, and also not to over-rely on external rewards all the time. And that to me highlights the whole reinforcement learning iterative process. It's not a one-time thing. The model is not only learning a policy, it's also refining its own understanding of what good reasoning is, and that allows it to continue improving by itself as it interacts with the world or even a simulated world. That is how we are going to reach AGI, in my view at least, It's this self-improving loop that's the key.
Self-improving? Isn't that just a bit too optimistic? I see these models as still being fundamentally limited by the training data and the algorithms we use. Yes, they can refine their search and maybe improve their predictions. But are they truly learning new concepts or just getting better at pattern matching on the data we have provided? I keep coming back to this. Are we just fooling ourselves with the power of the deep learning paradigm?
I think it's more than just pattern matching. If you think about it, the iterative search and learning loops can create a situation where new knowledge is being built from the interactions with the environment. It's like we are using an evolutionary system that, through search and self-evaluation, is iteratively building a better understanding of its world and better understanding of reasoning. It's not just memorizing solutions, but building the fundamental architecture for complex problem solving. It's like how children aren't just pattern matching what they hear. They're learning to construct an understanding of language and the world through interactions and feedback.
And that's the crucial link to learning that the paper talks about. It's not just about the search and the data. It is about how the model learns from the search data. It's an iterative loop. And I think it really emphasizes the idea that the learning method needs to match the kind of data it's getting. It talks about policy gradient methods and behavior cloning, which are essentially two different learning strategies. The policy gradient methods use all that search data, even the bad moves, to improve the policy, while the behavior cloning method learns from the best actions it takes during search. I feel that combining these would be the best approach.
But the paper also mentions that policy gradients are expensive and DPO. Direct preference optimization seems like the new hot thing, but again, we're back to preference data, aren't we? It's another way we are injecting our own bias through our choice of what we prefer, and we are moving away from truly autonomous learning. I mean, why are we using human feedback to train a reinforcement learning algorithm? Isn't that kind of cheating?
It's definitely a bit of a cheat, but it can also be seen as a form of initial scaffolding, providing guidance, a direction for exploration. The long-term goal is to move away from relying solely on human feedback and towards having the model learn more directly through the interaction with the environment. There is a trade-off here to make. We want models that can generate human-like text, for example, and human preferences are one way to guide models to generate that. The important bit is to figure out when to take off the training wheels and let the model become more autonomous, and also to figure out what a good environment is in the first place.
And in that context, the paper talks about behavior cloning, which isn't quite the same thing as the behavior cloning we have talked about before. Here, behavior cloning uses the search data as the expert data. This, in my view, is the more autonomous approach than the human preferences-based methods. It's about having the model imitate its own best moves through the search process, which aligns perfectly with that idea of an iterative loop of self-improvement and exploration that is driving advancement. It is the combination that is needed to reach AGI and to solve the scaling problem.
But won't this just lead to a system that's good at playing that specific reinforcement learning game we have designed? How do we make sure this isn't just overfitting to the training loop, that the lessons learned are not limited to the environment it was trained in? I mean, the paper is focused on how to achieve O1-like behavior. But what does it really mean to achieve O1-like behavior if it's based on a proprietary system we don't fully understand? Maybe we need better evaluation methods than just trying to copy what someone else did.
That's the crucial question for any model that aims for general intelligence. And it's true that we don't have a magic bullet for this, and we are still figuring out how to build a model that can adapt to any environment, any task. I think this paper really does a good job in highlighting what some of the critical components are, but also acknowledges that there is a long way to go. But it does mention transferability and generalization, and I think there are clues as to how this will be achieved. It is about going beyond the simple outcome rewards and building a more robust representation of the world and the learning processes within the model.
Exactly. I think we are at the beginning of a very exciting journey. The fact that we're dissecting these models into key parts such as policy initialization, reward design, search, learning is crucial because these are not just abstract concepts. These map directly to the way we build thinking machines. It's a structured framework for going about the problem and not just hoping it somehow works out. This roadmap is about being specific and intentional about the kind of intelligence we are trying to create. We're not just creating a program that solves one problem, we're creating a system that can think and adapt.
I hope you are right. I would love to be wrong on this. But I still feel we're missing something fundamental. I think focusing too much on imitation, whether it's human-like reasoning or replicating a black box model, might be a limiting factor. We need to be thinking about models that can truly explore, discover, and understand the world through their own lens, not simply mimic what we think it should be. It's the algorithms, not the data or compute.
Well, I think it is a combination of all these elements, the algorithms, the data, the compute, and understanding the fundamental principles of intelligence and how that can be expressed in these models and in brains. And also this iterative feedback loop to ensure these models can grow autonomously. But, like you, I do think there's a lot of unexplored territory and many open questions, which I find is part of the fun of doing this type of work.
All right, well, I guess we'll have to wait and see where this journey takes us. I'm still holding out for some groundbreaking new algorithm, but, progress is progress, even if we are just getting better at pattern matching.
Exactly. It's all about the journey and exploring those cognitive spirals. And thank you for joining us today. Let us know in the comments what you think about the direction of AI and the ideas presented here.
Yes, thank you, and please tune in next time. We have more exciting topics to discuss and explore.